Hey guys, this is Dilesh Pandey, and now I'll start with my topic, that is feature transformation. In feature transformation, we see various methods are there to transform data, and it is very crucial for us to transform our data set, since there can be presence of outliers. There can be several ways that we need to handle these categorical variables, because these categorical variables we cannot directly feed it into our machine learning algorithms. This need to be converted into a numeric way of representing a column. So first we will start by adding our data set. I'll add this customer and the data table, that too is in CSV format. Now importing our pandas library, numpy library and matplotlib library for visualization. I'll run this. Then if you see the data set looks like this: age, gender, review, education, and whether they have purchased something or not. Now it is very important for us to convert this categorical column into a column where there is a representation in terms of numeric. So there are several ways. Two ways which we will see is one hot encoding and label encoding, that we'll see their advantages and disadvantages as well. So one hot encoding is from pre-processing library of sklearn, and we have to make an object of this one hot encoder. This sparse output means there are a large number of zeros than the actual numbers. So this sparse output equals to false. This argument is important over here, because when we write this dot set output transform equals to pandas, this basically means that this column name will be coming when we will transform our data. So this extension is important, and this extension will only work when your sparse output equals to false. So one hot encoding basically does the things like, let's see data review column. Review column has average, good and poor. So there will be three distinct columns for average. Wherever the average is present, wherever the review is average, there will be a point as 1. Wherever there is poor is present, the point will be 1. Wherever there good is present, the point will be 1. And rest, let's consider the average one. If the review is average, then rest 2 will be 0. So the disadvantage lies over here only, because there is a dimensionality problem for using this kind of method, because you have end up including 3 columns instead of 1 column. This review will be divided into 3 columns. This gender will be divided into male and female, gender male, gender female. This education will be divided into education UG, education PG, education school. This purchase will be divided into purchase yes, purchase no. So your number of columns will increase to a larger extent. So this is not a very recommended way to transform your data. We have another way, that is label encoding. If you see the data, if you see data, this was our previous data. If we use the label encoder from preprocessing library of sklearn, here you can you have to fit manually for each and every column, but the thing is you can try several ways that you want to. I am using manually for this. The things are, you will convert these columns into you will not expand your columns. That is, review will be review only, education will be education itself, this average will become 0, this poor will become 1, good will become 2. So this is the way that label encoder works. Now I'll show you what had happened over here. Now if you see that dimension has not increased, but your tuple has changed. Your tuple has changed from records, has changed from the categorical column to numerical column, that is 0, 1 and 2. Similar cases for rest of the columns. So this is a very important thing that we did. Now there can be another scenario where you need to transform your data to reduce its scale, because there can be several problems you might face, just because some column has very high number. That is, if you see the price of house, area will be less, area will be, let's say, 2000 square feet, max to max 2000 square feet. Generally it's around 200 square feet, 300 square feet, but the price of this 200 and 300 square feet will vary for a larger extent. That is, price of 200 square feet will be more than 50 lakhs, more than 60 lakhs. So the difference between 200 and 50 lakh is very large. So the problem may occur like this. Machine learning algorithm may not understand the thing and weight, and makes the weight higher to the price section. So it will justify as the price is more important column than area. To avoid these problems, we'll use the scaling techniques. Again, from pre-processing, we have standard scaler. Now standard scaler is a technique that uses the standardization of the tuple. That is, if we have a column whose mean is 50, so for the current iteration, if the value of x is 60, so 60 minus mean divided by its standard deviation. Since this is a standardization technique, your mean will come to 0 because there is a mean deviation. You are taking deviation from mean, so you're taking deviation from mean will become 0 and your variance will become 1. That is properties of standard normal distribution. Now the range of this will lie between -3 to +3. It can go up above 3, but you should not consider the values above 3, since in standard normal table the last values that you will see is +3 to -3. Using this, now I think you know the dot set output transform equals to pandas, why it has been used. I'll show you without using this. Let's see what happens. So standard scalar on see, this is the kind of thing that you will see if you use this extension. Then I'll see it with columns, so no need of doing all those things. After applying this, no need to change it into a data frame and adding all those column names. You can just use this set output. Now we have another thing, that is Minmax Scaler. What Minmax Scaler does, and very important thing, standard scaler uses mean. So whenever you will use mean for your any kind of thing, it will be sensitive to outlier, since mean is sensitive to outlier. Okay, and another thing that accounts for Minmax scaler is, let's say you have a value of 50. 50 will be minus by 50 minus the minimum of that column divided by maximum minus minimum. Now here, since you use maximum, your values can contain the outlier, and outlier may have values that is very large. So using maximum can also be sensitive to outlier. So Minmax scaler is sensitive to outlier as well. Now transforming this, and you will see the value, some values has came over here. Now the good thing about this is it will transform the values from 0 to 1. Wherever you see the values, it will be 0 to 1. And for scale data, I told you values can differ, and values can be from +3 to -3, and you can see here the value is -1.16, that is it's exceeding from -1 as well, and it would exceed from +1 as well. So the range is +3 to -3. For the case of Minmax scaler, Minmax scaler will always be in the range of 0 to 1, because you are subtracting from subtracting from the minimum value. Minimum value will, if let's suppose the minimum value is 2, you are subtracting it from 2, that is you end up having the lower limit as 0. Now we'll see the scatter plot of age and education to verify whether the scaling techniques changes the distribution, changes the point, changes the plot, that how it looks. So this is the original data, and this is the scale data, that is standardized data. This is Minmax scalar data. If you see, you can verify all those 3 plots are same. Now we'll see for outlier detection, because outlier detection is also a very good problem, and that needs to be resolved as soon as you get the data set. Now we'll see the two techniques. If two techniques as removal means, if you have the outlier, that if you have outlier, you will just remove them. If you have outlier and if you do not remove them, you use capping. Capping means, suppose your limit for outlier is 75 and you have point that is 105, so you tend to remove them in removal. But in capping, you tend to change that value to lower limit, to change that value to upper limit, that is you will change 105 to 75. Now we'll define a function, that is box plot, that will take the data and the column name that you want to plot for a box plot. So this is a function that we created. Outlier, basically here we will see the points that are outlier, that is will define the interquartile range. Interquartile range consists of two things, q3 minus q1. q3 minus q1. q3 is the 75% of your data, and q1 is 25% of your data. Now 25 quantile of your data and 75 quantile of your data. Now the lower limit will be q1 minus 1.5 times iqr. I'll show you how this looks like in a plot, but for now just see as it is, and we'll find the index of column that is less than the lower limit, and the index of column that is lower than greater than your upper limit. We'll return the list. Now if you see here, I have written another function. I need to run this box plot. So this is the box plot. I'll make you understand this code. So basically your box plot you will plot in your numerical columns only. So I have selected the data. In the data I want the d types as float or integer, and these column names I have directed it into a list. So numerical column will look like this. So this is how my numerical column will look like this. Now I'll iterate over my numerical column names. I'll plot the box plot, that is this thing, and then I'll extend my out index. Since I have created the empty list for out index, for every loop wherever there is an outlier, it will get extended, and at the end I'll get the index of all those numbers who have either the value that is lower than the lower limit or greater than the upper limit. So these are the values that are greater than or lower than the criteria. I think you have got this. So now we'll see how to see this box plot. This box plot, this is the thing. This is the main box plot area. If this line is on the exact center, this represents the normal distribution. Here the data is slightly skewed towards right. That is, when you see the when you see this line exactly in the middle, this means mean, median and mode are equal. This represents normal distribution. But when you see all these points, these are considered as outliers. And what is this point? This and this point are lower limit and upper limit. Basically upper limit is here we have this formula q1 first quantile. This is first quantile, this is third quantile. First quantile minus this is first quantile, so minus 1.5 times interquartile range. So our range comes to 10. Now q3 plus 1.5 times interquartile range. So this is the value for this is the criteria for upper limit. So value exceeding upper limit are these values. So I think you are now able to see how to see the box plot and interpret the outliers. In this case you can see there is a standard normal distribution. See the point is exactly, line is exactly in between. A small distortion is accepted in normal distribution, because you will not get the data exactly that is normal. So this is the thing. Now we'll see there are 171 outliers. There are 171 outliers, and we'll drop the data that has these outliers. Now if we print the shape of data, we were having 569 568 rows, and after dropping we have 398. I will see the capping, how to do this outlier capping. Basically we will not delete the data, we will not delete the data or delete the row. We'll cap those values. If it extends the upper limit, we'll set it to a upper limit. If it is less than a lower limit, then we'll set it to a lower limit. I'll run this function. Basically this is the thing that we need to run. And now when we see the out index, list of out index, okay, we need to do something. Okay, so first we have to run this data. And now if you and now if you run this function, you should get 0 outliers. Not these two also. So this was the thing we need to run. We'll run this, and then again we'll run this. Now I will show the after removing all those outliers how our plot looks. See, every outlier has been capped, so there is no outlier present. See, wherever there is no outlier present in any of the plot. And if you print the length of the outlier index, that is 0. So this is the last thing that I wanted to inform to you all. Now thank you for listening.